ever wonder how a single server, just one box, can handle millions of us hitting a website at the same time without just completely melting down? Well, today, we're going to pull back the curtain on the kernel magic that really makes the modern internet tick. So here's how we're going to break it down. First, we'll talk about the big problem, concurrent connections. Then we'll look at the old, kind of clunky way people used to solve it. After that, we'll meet the hero of our story, epoll, and see why it was such a revolution. We'll peek under the hood at how it works, and finally, we'll see how it's powering basically everything you use online. All right, first things first, let's really get to the heart of the challenge that every single high-performance server has to deal with. I mean, this is the question, right? Think about it. When you connect to a server, it needs to know when you've sent some data or when it's okay to send data back to you. Now, don't just think about you. Multiply that by tens of thousands or even millions of other people. How on earth do you keep track of all that without just grinding to a halt? This is the I/O problem that desperately needed a better solution. So before our hero epoll showed up, developers had to make do with some, let's say, less than ideal methods. They were old and, as you're about to see, incredibly slow. The original tools for this job were a couple of system calls named select option and poll. Now, they've been around forever, they're part of the POSIX standard, which means they work on pretty much any Unix-like system, but they had a massive, critical flaw when it came to scale. Okay, imagine you're a teacher in a classroom with thousands of students taking a test. Using select or polling is like walking up to every single student, one by one, and asking, "Are you done yet? How about you? Are you done?" You'd have to keep doing this constantly for the entire class, even if only one person is actually finished. It's just so wasteful. It's exhausting just thinking about it, and it just doesn't scale. Yeah, that whole process was a huge bottleneck. So back in 2002, the Linux kernel introduced an absolute game changer. epoll was built from the ground up to solve this exact problem. Instead of your application constantly bugging the kernel asking what's ready, it completely flips the script. And the results, well, they're just staggering. And just look at this chart. This tells you everything you need to know. To monitor 10,000 connections, both select and poll took over 15 minutes. 15 minutes of just checking. But epoll, it did the same thing in less than a second. It's not even in the same league. I mean, that number right there, it shows you the jump in efficiency. This wasn't just a small improvement. It was a total breakthrough. It's the difference between waiting for your coffee to brew and a lightning strike. This is what made handling a massive number of connections truly practical for the first time. So let's go back to our teacher analogy. epoll is like the teacher saying, "All right, everyone, just raise your hand when you're finished." Now, the teacher can kick back, do some grading, and only needs to pay attention when a hand actually goes up. The work is proportional to the number of students who are ready, not the total number of students in the class. It's just an elegant, simple, and incredibly efficient idea. So how does epoll actually pull this off? What's the real mechanism behind the scenes that makes it so blindingly fast? Well, your application only has to use 3 main system calls. First, you create an epoll object inside the kernel itself. Then you tell it, "Hey, these are the connections I'm interested in." And third, you just wait. Your program basically goes to sleep, and the kernel promises to wake it up only when there's something that actually needs to be done. No more busy work. And this is the key. All the heavy lifting, all the hard work happens deep inside the Linux kernel. It manages the data buffers, it tracks which connections are ready to go, and it keeps this special ready list. As soon as a connection has something for you, the kernel proactively lets your epoll instance know. Your app just gets to sit back and wait for the good news. epoll is also super flexible. It gives you 2 ways to get notified. The default is level triggered, which is kind of like an alarm that just keeps on ringing as long as there's still data to read. Then there's edge triggered, which is more like a doorbell. It just rings once when new data first shows up. This gives developers really fine-grained control to build some incredibly optimized applications. Okay, so now let's connect the dots and see how this one kernel feature became the foundation for so much of the high-speed software we all depend on. You know, you could say that epoll is really the invisible engine that makes the whole asynchronous web possible on Linux. It allows a single thread to manage thousands of connections efficiently. This avoids the old, heavy way of doing things, which was to create a whole new thread for every single user. Can you imagine the overhead? It was a nightmare. And look, this isn't some obscure, nerdy detail. The absolute fastest web servers on the planet, like Nginx, are built on epoll. The entire Node.js event loop, it runs on this. The Go programming language, famous for its concurrency, it uses epoll to manage its Go routines. Even high-performance Python libraries use it under the hood. It is absolutely everywhere. So the next time you're on a super snappy website or using a real-time chat app that feels instant, you can give a little nod to a clever piece of engineering deep inside the Linux kernel called epoll. Understanding this isn't just theory. It's like getting a look at the foundational tech that makes high-performance, massively concurrent software even possible. It's the silent, powerful engine of the internet we use every day.